Hello, everyone. Welcome to today's research talk. Our speaker today is Tarun Chitra, founder and CEO of Gauntlet. Tarun is an alumni of D.E. Shaw Research, also known as DesRes, Vatic Labs, which is an HFT firm, and Cornell. He fell into the blockchain world in 2011 when he was working on ASICs at DesRes and observed Bitcoin ASIC mining rigs substantially delay DesRes's ASIC production. He has spent the last 7 years working on simulation-based R&D at the intersection of high-performance computing and AI, and is currently working to apply this knowledge to the blockchain ecosystem. Tarun's talk today is differential privacy in constant function market makers. Tarun, thanks for joining us. I will let you take it from here.
Yeah, sorry, the date is incorrect. It's actually September 30th. We have not time traveled. I think we're gonna maybe talk about this topic because I think it's quite prescient right now. I think there've been a bunch of people over the last 2 or 3 years who have sort of claimed to have made decentralized exchanges with various forms of privacy. But as we'll talk about, there's some impossibility theorems. You can't really do better than a certain amount. And this is sort of work that tries to get around those impossibility theorems in a particular manner using differential privacy, which is common in sort of like machine learning and statistical learning theory. So, we'll start with a little bit of history to understand what constant function market makers are. We'll give a little evidence and show that, they are the most widely used decentralized app by orders of magnitude. Pretty much nothing comes close. And so that's sort of one of the reasons it's actually really important to think about privacy in these apps, because there's basically none right now. Just to make it simple, assuming kind of the audience maybe has not thought a lot about how electronic trading works. Oftentimes we want to trade assets. One way of doing it is for one party to sort of make a offer to buy, and the other for a party to make an offer to sell. One way of aggregating all of the interest of buyers and sellers is an order book. Buyers post bids that are sort of the maximum price they're willing to buy for. Sellers post asks of the minimum price they're willing to sell for. And if a buyer's maximum price is greater than the seller's minimum price, then a trade is executed. Now, this is done in a centralized manner, naively, because there's sort of someone has to coordinate the storage and execution of these trades. So yeah, the first problem, trusted party keeping a record of outstanding bids and asks, and that has a linear space requirement where it's linear in the number of outstanding orders. When the highest bidder bids more than the lowest asker, price updates might be quite slow, which can be desired, but one of the reasons for that is you may have someone who's a gigantic seller, but each buyer only wants to buy a very tiny fraction of that seller's liquidity. And it doesn't end up moving the price, even though in some sense it should, the sort of notion of supply and demand on a quantity level might be matched. They're certainly not matched on a order by order level. And exchanges usually add subsidies to ensure there's ample liquidity. So one question is, can we actually replace human market makers, people who are posting buys and sells, with automated market makers where there's some sort of algorithm that does it? It's much harder to design these than other algorithmic systems, partially because you have to encode some notion of adverse selection. And what that leads to is that you have automated market makers that can only satisfy certain desiderata. So one is bounded loss. Maybe it's like the worst case loss that the market maker can hold. Another is sort of liquidity sensitivity. Fixed size trades move prices less when there's more liquidity, when there's more active orders. And then a small storage requirement, which is sort of like, I don't want to hold a ton of data relative to the number of orders processed. And there's a ton of impossibility theorems from like 2007 to 12 that sort of show you can't have all of these ever. So the first idea for an automated market maker was sort of actually done in the statistical literature in the 1970s. I think people in crypto certainly don't know anything about that literature, but it's sort of a very different style of why this was invented. It was invented for sort of these things called scoring rules, and scoring rules were sort of a measure of how you would compare empirical estimators, and completely different literature, but if you read the papers, it looks almost the same. They're really popularized in the modern era by Robin Hanson in 2002. This is sort of the thing that I think crypto people know of. They sort of know the log market scoring rule and prediction markets, because this sort of introduced automated market makers as a solution for prediction markets. One of the reasons that prediction markets are hard is that the event space is really large. So how do you provide liquidity to all events given a bounded budget? And so Hansen provided a certain solution to that. The idea is that liquidity providers, people who want to earn some yield on their assets from the market maker, pool their assets into the reserves, which is sort of, you can think of as pools that are either held in a smart contract or held by a centralized agent, whatever model you're looking at. If the prices are really low, an agent can buy from the reserves and sell externally on a different market. The prices are too high, the agent can sell to the market at a high price. When I say high and low, I mean always, in some sense, relative to an Oracle price external market, something like that. The idea is, like, given a function of the liquidity that people are posting, they're posting some notion of their valuation based on the liquidity that they're adding. You use that sort of aggregated information to set a price. So if there's a lot more of asset A relative to asset B, then asset B has to be more expensive than asset A in some sense. There's a couple examples. I guess the first example is sort of this fixed asset price at all reserve amounts that sort of has this sort of flat line structure. So that means, like, I'm willing to buy an arbitrary amount of asset A at $5. Another example is sort of the reported price of the ratio of the two. So remember, I said if asset A is more value, if there's more of that than asset B locked into the pool, it's worth less. The ratio naturally reflects that. The idea is a constant function market maker is meant to generalize these to a larger set of scenarios. So a constant function market maker is a contract with reserves, these kind of pools of different coins, A1 to AN. Liquidity providers supply these reserves, and traders are sort of allowed to add and remove coins, provided they keep some function of the liquidity, the reserves, constant. And for a bunch of reasons, there are some conditions on this function that exist. For sure, they're concave, not increasing. One of the reasons is, and we'll see this pictorially in a second, is that the epigraph, if you've ever done convex analysis, this is sort of just like a notion of the sort of super level set of a function. Is sort of the set of feasible possible trades in some ways. And the most popular choice is Uniswap. Actually, technically, for that to be concave, you have to take the nth root of it. That doesn't really affect the actual trading set. So why do we even care about this thing? Well, we can see there's roughly $3 billion a day of trading volume on these. They're by far they're the only crypto application of any form to ever have 1 million daily users. There's really nothing that comes close to it. I think, like, the lending protocols are in the hundreds of thousands. Layer 1 protocols are basically nothing, because the only users are exchanges and the development team and development teams right now. So, like, nothing even comes close. This is the only thing that looks like a traditional internet application, just based on volume and based on number of users. So let's kind of look back at this trading set. So this is the Uniswap trading function, xy equals k, or really square root of xy equals k. This is what its epigraph looks like. This is sort of the set of possible trades. So this is the set of trades that don't decrease the trading function value. And so that's sort of what the epigraph is. And so one reason you care about not decreasing is that it turns out if you add fees, you always end up increasing the constant. And only in the feeless case are you actually constant. So one way of unifying the case where the market maker charges users for using the protocol versus where it doesn't is to kind of look at this set. So we've only added points. So all the existing points that were feasible right on the super level set, on the level set curve are included. So technically it already includes the feasible set. No rational trader will ever pick a point inside because they're basically offering a free arbitrage trade back to the boundary. And this, again, is called trading set. One question you might say is like, well, who cares? Why does it have to be convex? Well, let's look at the super level set of a non-convex function. That means there has to exist some point where there's a tangent line that intersects the level set at 2 points. And that means there's two prices, because basically the price, if you remember, was the ratio. And so the price in some sense is the derivative of this implicit function. And if there's two prices, you might as well fill in the hole and just say it's constant across that regime. And that's basically what happens. Okay, now we can be a little more formal. So one question you might ask is, how does the shape of this function control how much people pay pricing wise? And the intuition is that the flatter the curve is, which sort of means the tangent line isn't changing very much, because if you think about the curvature of something from like calculus, it's sort of some notion of the relative rate of change of the slope of on a surface. The flatter it is, the lower price impact you have. But the sharper it is, sort of the higher price impact you have. Sort of the variance of the tangent line slope is much higher. So we can try to define something akin to this. And so we can define the price impact function as, if we do a trade of size delta, what is sort of the change to the slope over that trade size? And this delta prime, so R and R prime are the reserves. Delta prime is implicitly defined via the constant constraint. And you can think of G of delta as the change in price after a trade of size delta when you start at initial price, given an initial price. Because G of 0 is the slope of the function at the point R prime. And G of delta is, hey, what's the sort of like change in slope when I move to this new point? Think back to Calc 3, kind of basic Calc 3. Remember, when you have implicit functions, you can take gradients of implicit functions and you find that you get this kind of ratio. The main difference here is that we're choosing the negative, and that's purely so that prices are positive in a certain sense. But none of this should be kind of anything more than like basic multivariable calculus. So the curvature itself is represented sort of by Lipschitz bounds, both upper and lower, on this function G. And we say that a trading function is mu stable if it's sort of G has a Lipschitz constant of mu. And we say that it's kappa liquid if it's always greater than kappa times the size. So intuitively, mu stability means that given a trade of size delta, we'll never move the price more than mu times delta. On the other hand, if you're kappa liquid, given a trade of size delta, we'll always at least change the price by kappa times delta. So you might say, okay, well, this seems like a random definition. Why don't I just take the Hessian of the function? Why don't I take the condition number of the Hessian of the function? Why don't I take some other sort of local second order derivative information? And so this slide is really mainly focused on just giving you some facts to justify why this is sort of, at least on an economic level, the correct definition. The first question, so like when we wrote this first paper, not this paper, I guess like last year, that was around the time that yield farming and DeFi were really kind of starting to take off to the point that it was disrupting centralized exchanges. It wasn't quite at the billions of dollars of volume, but it was in the high hundreds of millions. And at that time, we started to see coins where the dominant liquidity source was not Coinbase or FTX or Binance, but was actually in one of these constant function market makers, where, for Sushi and Uni's case, in October 2020, I think more than 70% of liquidity was on chain. Very little was actually at centralized exchanges. And so one question you might ask is, if a constant function market maker, one of these on-chain automated market makers, is the primary venue, is the main place people are trading this asset, then, and there's sort of a notion of an oracle price, like this, imagine there's sort of this mythical infinitely thick order book that's the true price of the asset. Then how much does the primary market, which is now the constant function market maker, and the secondary market, which is sort of an order book or like another constant function market maker, how much can they deviate from the oracle price under no arbitrage? So people are constantly synchronizing the prices. And what we show is that in this definition of curvature, the ratio of mu to kappa controls sort of the maximum deviation from the oracle price. So in some sense, this definition is very good at classifying whether something is a primary or secondary market. And it also can help you say, like, you can't say anything about whether a price of a market is the true price, but you can say the following: if there were a true price, like sort of some oracle assumed price, then can I bound how far I am from that, given the prices of multiple markets? So if I know Coinbase's price, Binance's price, Uniswap's price, given the differences in those prices, can I bound how far we are from the true price? And this result sort of says like that you can, if you know these curvature constants tightly. The second fact is that given the trade of size delta and fees, so we didn't quite talk about how fees are implemented, but just for simplicity, assume that there is a mechanism where when a trader trades against the pool, there's a way for the liquidity providers to take a fee. And it turns out if they don't take a fee, they always lose money. So it turns out the curvature and the fee control the maximum trade size that can take place without the liquidity provider losing money. So that's another reason you care about this. Anytime you go on the internet, you see all these APYs and stuff for yield farming. All of those actually depend on this notion of curvature of like whether you can actually profitably achieve those or not. And the third fact is a fact from classical market microstructure theory, right? Like people won the Nobel Prize in economics for kind of proving this stuff, which is like in any market, if you don't have noise traders, so people who are trading back and forth randomly, you'll always effectively end up not profitable for market makers. Is that we kind of proved an analog of that result, which says that if there's an informed trader, so someone who can predict the next price always with probability greater than a coin flip, then the liquidity providers are only profitable if and only if there's some noise trader whose noise, like how much they're trading back and forth, depends on that probability, and it depends on this curvature. So that's these three facts sort of should at least try to give you a flavor for why this definition might be more natural than, say, I took the Hessian of this function, right? Because naively, you study geometry, you're like, oh, well, doesn't the Hessian or the Laplacian locally control the geometry? Why do I need this kind of weird implicit definition? Turns out to be that, like, if you want these sort of economically intuitive properties, you kind of have to unfortunately do it. So the first question is, are the noise traders trading with probability Q roughly equal to 1/2? As long as it's greater than 1/2, you're fine. I think hidden in this omega is some term that goes to 0 when Q is exactly 1/2. So that's a good point. Yeah. So the idea is that it just has to be greater, but the amount of noise needed So if basically as Q goes to 1, the amount of noise goes up a bunch. So this function is if you look at the actual definition, I just didn't want to write it because it's kind of a very ugly, messy function of Q and kappa. But it's in this paper. Basically, as the probability of the informed trader being correct goes to 1, then the LP needs higher and higher fees, which means it needs more trades back and forth because it's getting fees on every trade back. So it's losing money on the one informed trader's big trade, and it has to get a lot of trades back and forth, which earn it fees, which, you know, basically to compensate for that. But when it's near 1/2, it says it's close to a noise trader, so it doesn't need that many fees. That's roughly the intuition. But the idea is that informed traders, if there's informed traders, which, you know, could be insider traders, could just be people who are good at predicting things, whatever, then in order to be profitable as a market maker, you have to hope that there is also idiots trading. That's sort of if you read the kind of traditional 1980s economics papers, that they formulate it that way, where you have to kind of have, yeah, exactly. You have to have dumb money somehow. Otherwise, you will always lose money. It's a simple model, but it like gives you some vague intuition things. Also, so the second question from slide 17, if an asset is only found on dexes, how does that impact the ability to more or less bound the trading prices? And basically, how important are centralized exchanges for understanding these bounds? Yeah, so think of PA in this bound as the centralized exchange price. It's the Oracle price. It's like infinitely liquid in some sense. This says the relative prices between the dexes bounds how far any dex is from the true price, from the centralized price, if we treat the centralized as the Oracle price. So the natural next question is, hey, do we have privacy in these things? The answer is absolutely not. So there have been a bunch of designs where people were just like, hey, we're just going to post ZK commitments of the liquidity. So like every state transition will post a proof, but you can't see the reserves. You can't see the amount that's in the market maker. Is that sufficient for privacy? And we proved in this paper in March that that's not true. One of the reasons is that the convexity of this problem, you know, you might remember that, you know, if you have a convex function, strongly convex function, you have a unique global optimum, right? And there's a sense in which that's true here too. So even though these market makers have these amazing properties, like they have O of 1 state updates, unlike order books, that comes at a price. And the price is that you can invert what the state of the system is just from seeing the prices. So if I just see the prices and I know liquidity at one point in time, then I can invert precisely exactly the trade sizes that every participant made, without, even if you blind the reserves with a zero knowledge proof. This effectively says there's only two ways to avoid this. One is batching. So batching many orders together, executing them at once, so then people can't see. That has this problem of it's really bad for price impact, because what happens if I made a trade of size 1, but I get batched with 5 people who made a trade of size 500? Well, I'm going to be paying a lot more for the most part, right? And it's also worse UX. It takes a lot more latency, because you may submit a trade, but you may have to wait until enough other trades show up for the batch to close. The second thing is randomizing prices. So of course, this has worse price impact, but it also means that the end user has no clue what price they're going to get. And so if you do this, you have to provide some guarantees on, here's the trade-off between how much privacy you gain versus how much worse your price execution is. And that's what we're going to show differential privacy is actually good at doing. So one question, a naive question is, well, what if I just like randomly add random numbers to the price? Is that good enough? Not really, because let's say I add a bunch, you know, I draw CI, IID, I add them to the prices. Well, if they're IID and there's an upper bound on the third moment or the variance, of course, Bayesian CLT kicks in, and you can basically try to denoise the prices, figure out what the noise is, and then roughly get the prices back. And then you can, once you have that, you can invert. And so you actually have to add the noise in a correlated way that kind of moves with the price, with the trade sizes. So if there's a big trade, you need to add more noise. If there's a small trade, you add less noise. If you kind of add noise uniformly, it doesn't really help you. You can basically learn, you can kind of invert what the true prices are. This suggests we have to be smarter about this. So this is kind of where we get differential privacy from. Okay, so the natural thing that people in differential privacy and especially in machine learning care about, private machine learning, that is this notion of a privacy versus utility trade-off. So there's kind of, for things where you have private data and public revelation, like my trades, public price changes, like, so the price changes are all public, right? No one will use this market maker if the price is hidden. But I want to keep some of my information private. What this impossibility theorem shows is kind of what you see a lot in statistical learning, which is you can never kind of get both, and you always have this trade-off between utility, so how much worse of a price am I getting, versus privacy, like how many, what's the number of bits that an adversary can estimate my trade size delta I at. Batching is very good for privacy, but terrible for price impact. So on the utility price impact spectrum, it really is terrible utility-wise, great privacy-wise. So the worst case for batching is, suppose I have T trades, one is of size T, and the rest are all of size 1. If the trading function is kappa liquid, then that means the price impact I have is lower bounded as a function of T. So all the people who traded size 1, they now realize the impact as if they traded size T. So if T is really large, that sucks for them. They're just getting a really bad deal. Now, it depends on kappa. So if kappa is really small, maybe it doesn't matter, but of course that's why this definition is important for curvature. On the other hand, the raw just trading with no privacy, just like sequentially, is really great for price impact. It's very clear what the price impact is, known ahead of time, but it's terrible for privacy. So the goal is to try to say, hey, let's look at the two extremes, but let's parameterize strategies between those two extremes of everything's publicly revealed or it's completely batched, given some model of an adversary. So we assume a pretty simple but general model of an adversary. The adversary knows the initial reserves of the constant function market maker at time t. They can compute the price of the reserves at any time. So this basically is like they can always figure out what the price changes are. That's sort of prices are public statement. And the last query they're allowed is, given any trade size, they can query a trade delta and see if that trade's valid. You can think of this as sort of in the trading set, this kind of gives you a way of like locally searching and locally generating sort of a Boolean filter of like whether I'm inside the trading set or not. But notice that we don't explicitly know any identifying information about the reserves or any users. So that part could be hidden by ZKP, for instance. If you read the crypto literature and you read the machine learning literature, everyone kind of uses different names for the same thing. In crypto, they'll be called sort of adaptive adversaries. In machine learning and statistical learning theory, it'll be called online learning adversaries. In the differences, I think in crypto, people care about sort of like uniform bounds, whereas people in ML care about expected bounds. So there is some slight difference, but in general, they're roughly the same. So I'm going to interchangeably use those words. But personally, I guess prefer the online learning adversary. So let's consider this worst case trade for batching. So there's one trade of size T, there are T trades, one trade of size T, T minus one trades of size 1. The adversary wants to front run the whale. So they want to increase the price right in front of the trade of size T. And right after they sell back and decrease the price. And so This is called a sandwich attack. This is the most common form of minor extractable value that exists on Ethereum. And we're considering the case where it's actually harder than the normal sandwich attack on Ethereum. The miner or the protocol could, for instance, randomize the order of where T is. So it's sort of a probabilistic attack. So let's suppose the adaptive adversary, online adversary, learns T Boolean functions. And these Boolean functions are, I take the first I trades and it returns 1 if the whale trade is inside and 0 otherwise. Classical learning theory, this might kind of be a kind of obvious statement, but if the probability that if for all I, the probability that BI is correct, it correctly classifies this, is greater than 1/2, then you can use boosting to basically increase the probability to 1 minus gamma to the T, where the idea is like, you can basically combine your sort of weak learners who can learn with a slight edge, gamma, into an ensemble of learners who learn with a very high probability. If you've ever used gradient boosted trees, XGBoost, whatever, this is like what that uses. This is the theory for why that works, which sort of, I guess, is like every Kaggle contest. So what this shows is that the control of how the price noise affects the probability of these classifiers being correct impacts how likely the adversary will be successful. And in particular, this says the following: randomly permuting the trades actually lowers gamma. And so one of the reasons for that is when you randomly permute the trades, the adversary, suddenly the BIs have to have sort of less power because they're dependent on the ordering that they're given, right? There's a notion of BI depends on the sequence delta 1, delta 2, delta 3, dot, 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 delta I. So if I consider BI's performance on that sequence versus BI's performance on delta pi 1, delta pi 2, dot, 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 which is like the permuted version, it has to be lower. And so this kind of gives some intuition that permuting the trades does kind of lower an adversary's probability. However, one thing to note is that, in this kind of case of like one whale trade, there's actually not a lot of entropy from permutations. So there's technically T factorial permutations. But if you look at this function, there's actually only T unique outputs when I apply the permutation. T 1 1 1 1 1, 1 T 1 1 1 1 1, 1 1 T 1 1 1 1 1, etc. Right? So we've lost a lot of entropy, and so that's something that we also have to recover if we want to decrease the adversary's probability. One problem is that if you notice, this model of an adversary is tied to a particular instance or example, right? We chose an example, this threshold thing of like one size T, all size 1 trades, and then we constructed sort of a bad adversary. But suppose I give you a random sequence of trades. I'd have to construct an adversary for every sequence of trades who's kind of the best. So this sort of set of strategies is actually extremely high dimensional. It depends on the set of possible trade sequences, which is not good. You can't exploit much structure. Instead, we kind of want these like game theory style bounds of like mini-max overall trade sequences. Very recent and I think kind of very prominent and underrated work, probably due to the pandemic, that took place for the last 2 years, is that a bunch of theoretical computer scientists showed that online learning bounds are very closely related to differential privacy bounds. So if you have an algorithm that's differentially private, we'll talk about the definition in a second, you can basically bootstrap an online learning algorithm that's the best case adversary against that. In some sense, differential privacy and online learning are sort of the two sides of the same coin. So what this says is, oh, actually, if we prove differential privacy, we actually get worst case online learning bounds. So we can kind of have this intuitive picture in our head of this adversary doing this type of thing, but we don't have to prove it by using that model, because that model is terrible, or it's terribly hard to prove things. Okay. So what is differential privacy? So privacy comes in a lot of different shapes and sizes. I'm sure everyone on this kind of call knows ZKPs, computational proofs. Given an NP program, I can construct a sort of PCP style result. I can compress it a lot now, etc. They're cheap to verify. They're sort of extremely hard to do on learning algorithms, but at least they're kind of having this Moore's law, or sort of had a Moore's law for a couple of years. Homomorphic encryption, you can compute on encrypted data, extremely hard, very far from production, very unlikely to be the solution. Differential privacy. So this is the most used privacy preserving mechanism, period. So if you have an Apple phone, every time you use Face ID, it's doing a differentially private version of Face ID. That's how it updates its weights. If you've ever filled out a US Census form, also does differential privacy when sociologists get the data to analyze. And what it does is it's basically, hey, I'm going to add a bunch of noise to people's data, so it's hard to identify an individual. So we can't figure out who a single individual's impact on a statistical estimator is. It's very easy in practice on hard algorithms, because the complexity of adding privacy is much less than the complexity of the algorithm. So one problem with zero knowledge proofs is sometimes the complexity of constructing the circuit, compiling the circuit, generating the whole system to do it is much higher in complexity than the actual algorithm that you're trying to blind, which is one of the reasons it's very hard to do these types of things. Okay. So what does differential privacy look like in pictures? Suppose we have two data sets, one with n people and one with n-1 people. And the one with n-1 just removed one of the people. And let's say each person, the function f computes the average height of the individuals, but it does so by adding some randomness to each person. So intuitively, when you're differentially private, if I remove any individual, let's say there's one individual who's 7 foot tall and everyone else is sub 6'3". If I remove that individual who's 7 foot tall, they will change the average quite significantly, right? So when I look at the average, I'm like, oh, wow, the person who was removed must have been large enough to have caused this amount of a change to the average. So what differential privacy says is, hey, you actually add randomness to everyone's height. So now on average, everyone's height's less than 6'3", but with high probability, there's someone whose height is accidentally 6'8" in the average, such that even if I remove the 7 foot person, the probability that the output average height is different regardless of who I remove is quite small. So the idea is you add noise to compensate for each individual's privacy. Formally, an algorithm is epsilon delta differentially private. Actually, this is a slight error. An algorithm is, a randomized algorithm is epsilon delta differentially private if for all x and x prime in the domain that differ by 1. So you can generalize the definition of, hey, I just removed a random person, to, hey, I have a metric space and I took a unit ball. And all measurable sets in the domain, so the measurable should be moved over there. I have this property that the output of the algorithm, the probability that I get a certain set of results, a set of heights, is sort of close to the neighboring one, even if the neighboring one changes some of the data, like removing a person, changing one person's data. And the epsilon, you could think of, if you think of just like classical learning theory, is just a uniform bound on the pointwise KL divergence between the two distributions of the output of the algorithm. And the reason for that is, suppose delta is 0, take the ratio of the probabilities, take the log. So now you have log of probability of 1 over probability distribution 1 over probability distribution 2. What is that? That's nothing more than a term in the KL divergence. And we're saying that's upper bounded by epsilon. So it says that these two distributions are close in a multiplicative sense, which you can see as this in the figure as the ratio is bounded by e to the epsilon. That is in the KL divergence sense. And then delta is sort of like a measure of error probability. What's the probability that they aren't close? And so the reason you care about this closeness is you say, hey, I randomly mutate the distribution. I mutate the input data to the algorithm, but the output data from the algorithm stays, the distribution of it stays kind of close to each other, except on some number of examples. And you think of delta as cryptographically small, like 2 to the minus 256. Close to the error of a SHA type of thing. Maybe it's a hash collision, so 2 to the minus 128, whatever. Choose something very small. What does it mean to be a mechanism in differential privacy? For some reason, people call it a mechanism. It's just any randomized algorithm that achieves that property. And the randomization is quite important, of course, because we're talking about KL divergences and approximate and kind of errors of KL divergences. So I take a function, I take privacy parameters, a data set, and I output this private mean, like this average height over the data set. One question is, can we do it in a generic way, given an arbitrary function and an arbitrary sort of average I want to take? So there are two main mechanisms. One is called the Laplace mechanism. So this is actually what I'd say the majority of practical implementations use. I think some of them might use the Gaussian mechanism. And the Laplace mechanism says, hey, for every element, every pair of elements who in the domain who only differ by 1 in your metric. So your metric could be, it could be a Hamming distance type thing, like I removed one of the data points. It could be an L1 metric, it could be L2, it could be any metric you want. And now consider maximizing the difference in function value over any neighboring points of the data set. So that's what the point of this kind of like localizing the neighborhood thing is. So it's like, what's the maximum deviation between any neighboring points? And now take your data and draw random numbers from a Laplace distribution. So a Laplace distribution is simply exponential random variables symmetrized across the axis, like that. Whose parameter, so whose width, is this maximum distance divided by epsilon. And you can show that if I take the average of the function evaluated at the noised points, I'll achieve epsilon differential privacy. And if you instead replace the Laplacian with a suitably chosen Gaussian, you only get epsilon delta. Part of the reason for that is the definition of differential privacy has this exponential in it. So if you have something whose tails decay faster, then obviously your KL divergence bound is never going to be uniformly true, just from kind of like looking at intersections of distribution tails. There's another thing called exponential mechanism, which is basically a way of sort of like a way of random sampling out of a data set, but we don't use it in this work. So one of the key things, and I think this is quite important for DeFi more than probably anything else in decentralized crypto land, is that differential privacy has composability properties. And these composability properties are extremely important to its stability. So one thing is that if I have a sequence of differentially private algorithms, and I say, hey, I take an input, run algorithm 1 on the input, get the output, run algorithm 2 on the output, get the output, run algorithm 3 on the output, continue sequentially. And each algorithm is epsilon I differentially private. Well, the sequential composition will be the sum of all the epsilon i's. And if you have a bunch of parallel algorithms, then you basically get the max. So you kind of get this like semi-ring tropical type of structure. It's not quite that in some sense because you can't take limits. So it's not an algebraic algebra of algorithms, but it sort of has a flavor of that. Well, one problem you might say is, hey, this delta F, this thing that you're adding the noise, which controls the width of the noise you're adding, that thing could be gigantic. It could be greater than the average by like a million. So then who cares? You just added so much noise that like the data doesn't, the output height doesn't matter. Like let's say in the height example, delta F was 5 feet. And let's say most people were between 4 feet and 6'3", except for this one outlier who's 7 feet tall. Well, if I'm adding noise whose width is 5 feet, then I'm going to distort this data of the sample significantly, right? And this sort of max pair thing it might be 5 feet because there's a 7-foot person and there's someone who's, well, 2 feet tall. And that worst case data point in the data set controls the noise you add, and it's bad. It's a global. So one thing you might say is like, hey, given the 7-foot person, maybe I add a lot more noise. And given the 2-foot person, maybe I add a lot of noise. But if you're near the median, maybe I don't really add that much noise to your data. And so one question you might say is, can I do local sensitivity? Can I add noise only to the outliers, and then people who are not super in the outliers, or data points that are not in the outliers, don't need that much noise? A natural way to do it is you say, hey, I'm going to do local sensitivity. Given a point, I'm just going to look at my neighbors, and I'm going to look at the maximum distance between me and my neighbors. So if I'm the 2-foot person, I look at the max distance, and okay, the nearest neighbor to me is 5 foot tall, so I have to add 3 feet of noise to my data point. But if I'm in the 5-foot range, my nearest person is 5'2", so I only need to add 2 inches worth of noise. I'm giving units to make it feel concrete, but it's, you know, if you write down the equation, it's not exactly unitless, or not exactly unit filled. But so the idea is that each data point will get slightly different noise based on like how close they are to other data points. And you know, if we take the maximum overall data points, we actually can recover our global sensitivity. So the idea is that the 7-foot person will be adding 5 feet of noise, no matter what. But only then. Everyone else will be adding less. So it turns out that this naive definition doesn't work, but there is a way to make it work with some error. And this is this mechanism called smooth sensitivity. Not going to go into too much detail, but that is the thing we use here. Smooth sensitivity also lets you generalize to a larger set of metrics, and you know, we'll get to that in a second. Okay, so finally we are at how do we relate all this random probability stuff I've thrown at you back to automated market makers. So the main result, let phi be a kappa liquid and mu stable trading function, sequentially processing a sequence of n trades. Suppose that we have a verifiable source of randomness, like a VDF, VRF, either of those. Then we can achieve mu is, remember, the upper bound on curvature, upper bound on price impact, times log of the number of trades and little o of 1 differential privacy. So this says that there exists a way, given a random oracle, sort of like a VRF, to turn, to kind of achieve differential privacy, and we'll go through the mechanism. But the main thing to note, and I think this is the most important thing, is right now, in every smart contract language, there is no way for a developer to take the output of the VRF and sample from distribution. So like, let's say the VRF draws a string of numbers. If I'm writing an application, I'm like, I want a verifiable sample from a normal distribution. I can't do that right now because of like how smart contract languages are structured as separated from consensus. So this protocol mechanism described here requires the smart contract to be able to get that. And so I think like that will need some design changes to existing smart contract languages, but not crazy ones. And so we need 3 types of random samples from VRF. So when I say random sample from the VRF, this is precisely the thing I'm saying. VRF is drawing a uniform sample from on whatever space it is, whether it's on elliptic curve or whether it's on integers. But suppose I could take that and black box construct verifiable samples out of these 3 distributions, the Laplace distribution, the uniform distribution over the symmetric group over permutations, random permutation, and the Dirichlet distribution. The Dirichlet distribution is a distribution over random distributions, discrete distributions. So it's sort of a distribution on the simplex. So the main thing that we use to prove this result is something called the trade tree, and we'll look at it in pictures, but it's constructed from partial sums of the following form. So take a permutation, sigma, and now permute all the trades. So delta sigma of I is the ith trade after permuting under sigma. And now consider the deviation of that trade minus mu over kappa. Again, this mu over kappa is a very important sort of condition number that shows up in a lot of places. Minus mu over kappa times the original trade. So let's say I had the trades 1, 2, 3, and I draw a permutation 3, 2, 1. Then the first thing would be trade 3 minus mu over kappa times trade 1. The second one would be trade 2 minus mu over kappa trade 2. And the last one would be trade 1 minus mu over kappa trade 3. If mu over kappa is 1, you can basically look at this as a notion of discrepancy. Like under a random permutation, how much what's the net change? And obviously, when mu over kappa is 1, if I sum this, the I sum will be 0 in trade flow direction. And the mu over kappa sort of naturally shows up as a way to rescale based on the curvature. This tree is constructed by inserting these row i's into a binary heap. And you can think of it as, again, this trade size discrepancy. The mu over kappa is to account for the relative price impact after randomly shuffling the trades. So this is kind of what this trade looks like. This tree looks like, it's just like a normal binary heap. But it allows you to say, hey, after I did the permutation, given a particular permutation, I'm ordering how much discrepancy I caused to the ith trade. Like how much under that permutation did I make their trade worse or better in terms of flow until that point, which is price impact. It turns out you can try to say, hey, look, I want to maximize, I want to find the person who's traded who had the worst impact. So like I randomized the order. Let's say I had the trade of size T and then a trade of size 1, 1, 1, 1, 1, that bad example. Now, if you were a trade that was previously a trade of size 1 after the whale trade, and then you got moved before, you got positive price impact because you got to trade before the whale. So like you didn't get kind of run over by them. On the other hand, if you were before and you went after, you got run over by them, right? So this is saying those people, the maximum are the people who are on the bad side. The whale kind of got in front. They went from before the whale to after the whale when I shuffled. So it turns out for a given sigma, you can bound it by the value at the root plus the sort of maximum discrepancy over all these things times the height of the tree. And now we can say, hey, this is an upper bound. Let's take the expectation over random permutation. Because the mechanism, what it really does is it randomly permutes the trades and then breaks up the big trades. And what you can show is if the root has constant size, and we can bound the second term by log n, then we actually have an exponentially better mechanism than batching. Remember, batching was lower bounded by linear in t. Sorry, n and t are the same here. Lower bounded by linear in t. But here we can get logarithmic in t. And so that is a huge improvement price impact wise, like in a sense on average. We also want a lower bound, like on this quantity, and it turns out that's also related to the height of this tree. So how do we ensure that this thing has height log n? Well, we add a bunch of noise. So we add noise to each trade. And then if trades are really big, we split them. So we do three things. We first add noise to trades. Then we split up the big trades. And then we randomize the order. And doing that, you basically can get this guarantee. And some technical details, like you can actually like do this Dirichlet sampling privately. Why do you care about being private? If it's not private, then like you might be actually leaking exactly how you're cutting up the big trades, and then people can look for signatures of that. But it turns out you can do that privately. And remember, differential privacy has this composition law. So what you do is you show permuting is differentially private, then splitting is differentially private, and then adding noise is sort of naturally differentially private. And so you can compose those three and you get the final result. And so the last thing, I know I'm a little over, is can you do better? And so unlikely. So the thing that inspired me on this construction was this idea of differential privacy and online learning have this equivalence. If you try to, the thing that links the two of them is actually the height of a certain type of tree, which is what led to this construction. And this tree bounds the height of that tree, which bounds the complexity of an online learning algorithm. And effectively, if we did a lot better, you would have sort of like a sub-exponential algorithm, learning algorithm, which would be bad in some other sense. Because like that would mean someone could actually learn without actually having to go through all the subsets of trades, unless there's no curvature. And the next question is one thing I kind of hid here is we didn't really talk about fees. One question is, can you handle fees? There are ways of doing metric embeddings of these trees and then using something called generic chaining to try to do this. We kind of sketch a little bit in the appendix, but not fully all the details, but it should be possible to complete those. The idea is you can get privacy if you're willing to pay a randomness cost and you have verifiable randomness. You know, what's the utility privacy trade-off? Well, we can actually try to write down how much entropy we need. And one other question you might say is, well, if you're adding differential privacy, you're sort of lowering MEV. You're reducing the chance that you get sandwiched. So there's this natural trade-off there. And so one question is, can you actually quantify that? Cool. Before questions, I can give some references since it's recorded. Cool.
That was really awesome. That was something that I'm eager for our like heavy crypto economics folks to take a look at and hopefully reach out to you to continue kind of questions or conversation. It's great to have you. We'll be in touch to follow up, but really awesome talk, and we'll reach out soon. Thank you so much.
Yeah.
Thanks for joining, everyone. If you have suggestions for a future speaker, or if you'd like to present your own research, please email us at research@protocol.ai. Please remember to like and subscribe and share this video. If you want to receive emails about funding opportunities, future talk announcements, and general updates on Protocol Labs research, sign up for our mailing list. The link is in the footer at research.protocol.ai, and I've also pasted it in the description below. Thanks again for joining, and we'll see you next time.